A new cosmic giant, 100 times bigger than 3I Atlas, has burst into the solar system. One interstellar wanderer has already shocked scientists, and now a second one has appeared, 100 times larger, with both of them moving toward the sun on almost the same path. Coincidence? Or is there something more behind it? Imagine this. The night is clear, the sky calm, telescopes silent, and then, one after another, instruments all over the world begin registering events that don't fit the familiar picture. First came 3I Atlas, an interstellar visitor whose tail already forced scientists to reconsider what they thought they knew about comets. And just as it seemed we were beginning to unravel its mysteries, a new player stepped onto the stage, a massive object given the working name Swan. Its trajectory strangely overlaps with Atlas's path. Two large bodies, one interstellar, the other a giant comet, have ended up at the same coordinates not by coincidence, but almost as if by design. This isn't just another astronomy item. This is a chain of signals raising a cascade of questions. Why do the tails behave differently from textbook models? Why do the spectra show unusual element ratios? Why do the orbits display tiny but systematic deviations? Is there a natural physical connection between these objects? Or is there something more deliberate behind them? We'll go through the key facts, the timeline of discovery, and the data observatories worldwide are collecting. We'll examine possible explanations from rare orbital geometry and exotic composition to scenarios involving maneuverability or even technological traces. In the end, we'll ask, should we be afraid? Or is this a chance to witness something previously only theoretical? It started with sky surveys recording 3I Atlas, a hyperbolic trajectory, an unusual tail, and strange spectral features. While scientists were still analyzing the first data, a new large object appeared along the same survey lines. Nicknamed Swan, it was spotted as a large, bright comet with a powerful coma and periodic outbursts. Preliminary calculations showed its size and brightness far exceeded most recently discovered bodies. Signals about Swan came from several independent observatories, including a survey network in Chile. Atlas, automatic telescopes, and several amateur stations confirmed the object was real and rapidly evolving. Within days, more powerful instruments joined the effort. Ground-based giants and a space telescope performed preliminary spectral measurements. The first spectra and photometry revealed anomalies, brightness outbursts, unusual tail profiles, and small deviations in orbital trajectory. These measurements require verification, but one thing is clear: this isn't a typical quiet comet. Alarmingly, preliminary orbits show Swan and 3I Atlas appearing to intersect in the coming weeks. Such a spatio-temporal coincidence is statistically rare. Scientists immediately coordinated efforts. Teams shared observations, built detailed astrometric models, and planned targeted monitoring across wavelengths. The priority: gather as many independent data points as possible. Optical images for coma shape, spectra for chemistry, infrared for thermal profiles, and precise coordinates to detect any non-gravitational accelerations. Swan's discovery doesn't look like a banal coincidence. This event demanded an immediate scientific response. Every new image or spectrum could radically change the picture and move hypotheses from maybe to proven. Telescopes worldwide are recording not only appearances but inner signatures, spectra, composition, and tail behavior. Swan and 3I Atlas share disturbing traits. Normally, a comet's tail is a diffuse jet of dust and gas blown away from the sunday. Here, we see narrow, directed structures that persist for days. They don't dissipate under solar wind but remain dense, as if fired from a focused source. Time-lapse footage shows these jets stable in profile, while neighboring tail fragments behave normally. Spectra from James Webb and ground observatories revealed anomalies that don't fit cometary literature. The CO2-Rs to water ratio in 3I Atlas was anomalously high, several times above normal comets, indicating a composition dominated by unusual volatiles. Moreover, spectra showed elevated atomic nickel with a notable deficit of iron, a combination practically unheard of in our solar system. This chemical profile suggests formation in a different environment or exposure to unusual thermal and chemical processes. Particle size distribution adds another oddity. Reflected light and polarization analyses indicate tails contain large, dense particles that don't sublimate as fast as fine dust. That explains the jet's long-lived stability, but not why emissions originate from the sun-facing side. In simple sublimation models, even exotic compositions shouldn't produce such focused, sustained jets. Radio monitoring for structured signals so far found nothing. The absence of repeating radio patterns reduces the likelihood of an artificial origin, but does not exclude technological traces, especially if autonomy or stealth is involved. In sum, tails and spectra show unusual chemistry and jet structures, but no single explanation fits all observations. Scientists began tracking both trajectories with extreme precision. Hundreds of observations from diverse observatories were combined to map routes. Then, something strange emerged. Normally, celestial bodies move under gravity, predictable to high precision. With Atlas and Swan, predictions began to fail. Between predicted and actual positions, small but consistent deviations appeared. These shifts were too systematic to be mere instrumental error. They resembled a subtle, steady push, as if an unseen force nudged the objects. The direction of these nudges matched the orientation of the anomalous jets, suggesting a link between outgassing and trajectory changes. It looked less like random nature and more like guided motion. Three families of explanations arose, each plausible but imperfect. Purely natural mechanisms. A localized, highly volatile patch on a nucleus could produce a narrow, stable jet. With the right rotation, this jet might act like a small rocket, producing non-gravitational thrust. Variations in porosity and particle size could create persistent, dense streams. However, current simulations with varied ice mixes, particle sizes, and outflow rates failed to reproduce the full set of observed features simultaneously: a long-lived, sun-pointing jet, plus steady, orbital acceleration. Interaction. The objects might not act in isolation. An ionized gas cloud, strong localized magnetic fields, or outflows from one body could influence the other. Both could be passing through an interstellar filament with unusual properties. This would explain synchronicity and correlated trajectories better, but it requires observational confirmation, for instance, correlated brightening or timed responses between the two. Propulsion and control. A continuous jet functioning like a natural engine is one natural variant. The more controversial option is artificial propulsion, an onboard system producing directed thrust. This hypothesis explains focused jets and precise orbit corrections, but requires direct proof. Structural features, transmissions, or unmistakable maneuver sequences. So far, no such proof exists. Scientists treat the control hypothesis as extraordinary and only to be considered after exhausting natural and interaction scenarios. We recall lessons from Oumuamua and Borisov. Oumuamua, 2017, surprised with no tail, an odd shape, and non-gravitational acceleration, prompting months of debate and exotic proposals. Borisov behaved like a normal comet, reminding the community that interstellar visitors vary widely. These precedents taught astronomers to demand independent confirmation and to prepare for surprises. That caution explains the current global coordination. NASA and ESA request telescope time. VLT, Gemini, Keck, and other giants perform targeted imaging. James Webb provides infrared spectra. Radio arrays listen for structured signals. Amateur networks supply additional astrometry. Scientists are watching for orbital changes, new outbursts, shifts in tail composition, sudden brightness spikes, or repeating patterns. Special attention focuses on conjunctions when observations are blocked by the sun intervals that are both observational blind spots and windows where deliberate maneuvers, if any, could occur unnoticed. After reemergence, critical data will reveal whether trajectories, activity, or spectra changed. So where does that leave us? Two massive objects, overlapping paths, abnormal tails, unusual chemistry, and small systematic orbital deviations. Natural explanations exist. Interaction models remain possible. The technological hypothesis lingers as the most controversial. At present, data do not provide a definitive answer, but the coincidences and anomalies are enough to force scientists and the public to watch the skies more carefully than ever.